It's my pleasure to introduce Andrey Krutov, who's one of our own here at the Czech Academy of Sciences, and he will talk about joint work in progress with Pavle Pajic on the cubic Dirac operator for UQ-SL2. Go ahead, Andrey.
Okay, thank you very much for introduction. Yeah, so it's some piece of joint work with Pavle Pajic about cubic Dirac operators for quantum groups. As today it's Students' Day in Russia, so this talk will be a bit introductory. So I will review a classical situation and recall a couple of things in the classical picture that we want to quantize, and then I will present some calculations for a Dirac operator, and it will be the end of my talk. So, and yes, I want to give a special thanks to Branimir Chacic, who inspired this work, because some discussion with him was a main motivation to consider this problem. So thank you, Branimir. Let's start. So, section 1, G differential spaces. And spaces and algebras. So I will speak about algebraic counterpart of so-called Cartan model for homogeneous manifolds. The essence of this model is a following construction. So let G be a compact, to be safe, connected Lie group. With Lie algebra that I will denote by mass fraction. Then to this algebra, to this Lie algebra, we can associate a Lie superalgebra. So that will be defined in a following manner. First of all, it will be denoted by G hat, and it will be Z graded. So it will have three homogeneous components of degree -1, degree 0, and degree 1. And these two guys are odd. These guys is even. Now so it's a Lie superalgebra. With the following commutation relation. So if we look at G0, then it's spanned by symbols that I called Lx, which is parameterized by elements of my original Lie algebra G. And as a Lie algebra, because it's a zero part, even part, it just isomorphic to my original algebra G. -1 part will be spanned by odd elements that I will call Ix, again parameterized by elements of my original algebra G. And okay, maybe I should. And it's isomorphic to G as a G module, and my 0 part, 1 part, it just spanned by single element that I will denote D, and it will be What is a commutation relations in my algebra? So if I will want to commute two guys from the 0 part, I just took the commutator of X and Y. If I want to commute L with 0 part with -1 part, so I use a model structure on a -1 part. So it's I of the commutator. And the last identity, but not least, is how I commute the commutate the i's the contract, which is later become a contractions with a differential, it will be just my else. So the motivation for it is a Cartan magic formula. If you remember, if you have a Lie derivative of a vector field, then it could be written as the following expression in terms of Dirac differential and contraction operator with respect to our vector field. So our motivation, Cartan's magic formula. But I will discuss it a bit in details later. So, for example, if we have a G manifold M, then there is a natural representation of our Lie algebra G hat, a Lie superalgebra G hat, on the space of differential forms on this manifold. So my L's becomes Lie derivatives, my I's becomes contractions with the corresponding vector fields. I could write these vector fields explicitly. So they're just generators of the action of my Lie group. And my D, in this sense, is a Dirac differential. So it's a particular case of more general construction that I will call G differential algebras, and gonna to define it in a minute. So definition. A G differential space yes. No, because it's a supercommutator. Your contractions and Dirac operator are odd. So it's exactly this case. Well, anti-commutator, it's have a plain sentence. So a G differential space is a superspace. For people who are not really familiar with the super stuff, it's just Z2 graded space. Vector space. Together with them, the structure of representation of my Lie superalgebra G hat on Lie superalgebra of endomorphisms of it should be, of course. I will use some notation in future. So B horizontal will be the guys who invariant with respect to minus first part. So the guys who killed by contractions. B invariant will be, of course, guys who invariant with respect to zero part. And basic elements will be intersection of these two Bosnians. And a G differential algebra is a super algebra okay, super here just refers that we have a Z2 grading here. Together, so is a super algebra B plus representation of our G hat such that it takes value not now just in any endomorphism, but in derivations of our algebra. So I will show you a couple of very natural examples that also appear in geometry. So first example, consider as a B exterior algebra of the dual of our original Lie algebra G. Then Lie derivatives just act via co-adjoint representation of G. So we know that Lie algebra is a module over itself. We can construct, so it's called adjoint representation. So now we can pass to the dual module. It will be co-adjoint representation. And then we extend the action of our original Lie algebra to the exterior algebra by derivations. So of course it should be graded derivation. So you have a plus minus sign, but standard business. And the contraction operators are defined in the following way. Suppose we have F, which is element of a dual Lie algebra. And these guys are generators of the exterior algebra of a dual. So how my contraction acts? Well, just evaluate F at X, or sometimes I will write in this notation. And then again, extend this by derivation. So just usual contractions that you can define, for example, for tensors, and then pass to the quotient. So nothing exciting. But what about differential? Well, first of all, let us know that we can identify derivation of this algebra in a following manner. So it will be homomorphisms from G star to the exterior algebra of G star. Well, this holds because we can define that every derivation is determined by the action on the generators. So, and generators is exactly this guy. Then consider the element that lives in this home. So it will take value not in the whole exterior algebra, but in the second power. So it's some subspace here. Which is defined as a dual to the Lie bracket. So to the bracket, because the bracket should be skew symmetric, we can think about it as a mapping from exterior algebra of, from the second exterior power of G to G. So what is dual? It precisely means the following. So if I have a F which belongs to the dual of Lie algebra and two elements from the Lie algebra, then the following identity should hold. So if I will contract with X and Y, the guy that is called dF, then it's just evaluating F as a commutator of X and Y. And in this setup, I claim that position, the exterior algebra of a dual Lie algebra is a G differential algebra. Just a small comment, if you want, if you will, for example, explicitly write the condition for D to be a derivation, then this D square will be exactly equal to Jacobiator of the bracket. So if the guy, the bracket that we started satisfied Jacobi identity, then this differential will be equal to 0. And you could probably already recognize this guy. It's just a cohomologies of our Lie algebra with a trivial coefficients. So if you consider cohomology of this complex, then it's usually denoted by this symbol. So it's our differential is just Chevalier-Ellenberg differential for our Lie algebra. And if our Lie algebra is reductive, then we have a nice mapping. So this mapping exists for any G. But if it's reductive, then it's isomorphism, and we can speak about the homologies of our G. So it's one of the first motivations that lead us to the geometry. So considering some invariants here in our G differential algebra, we can obtain some information from the cohomologies of our group. Okay, good. Now let's go further. Check my time. Another example is a Weil algebra. So it's defined in the following way. So we should take symmetric algebra of G star and tensor it with stereo algebra. Then I will not speak much about this guy. Well, I will not give so much details. Lie derivative could be represented in the following way. So symmetric algebra will be again a module over our original algebra G. So we can define the action here just by the Leibniz rule. And our contraction will contract only something in the exterior part. And the rest I will leave a bit mysterious, because differential in this algebra will be sum of two differentials. One is called Cajole, another Chevalier-Ellenberg. So this Chevalier-Ellenberg comes from exterior guy. And the Cajole differential, well, you can think about these two guys as this guy as a Cajole algebra. And for such guys, you can define a mapping that will be differential and morally will send generators from here to here. And generators here will send to 0. So you can see that it will be at least, its square at least will be, yes. Well, I may be cheating because this Cajole differential, it acts on the whole guy. If you remember, this guy is a Cajole dual. So, and this guy, I check in Chevalier-Ellenberg differential, I extend it to these values. So it's really a sum of not tensor product. And probably it's better to use next time microphone. Okay, now, this guy appears when you want to speak about some transgression, famous theorems by Cartan that allows you to calculate some cohomologies of homogeneous spaces. And I will speak about one instance of it. So it's equivariant cohomologies. Or about the algebraic contrapart. So first, if I have a two G differential algebras, then the tensor product is a G differential algebra again. Let me just stress that the tensor product here, it should be taken in the category of superalgebras. So we should take care about the signs. So we could, it will be important later because well, the category of superspaces is a braided monoidal category. So we have a natural notion of a multiplication of tensor product of two algebras. And then we will pass, when we will pass to the quantum case, it will become a bit more complicated. So, okay, now definition. The equivariant cohomology of G differential algebra B. So is cohomology of the following complex. So it's denoted by H subscript GB. So let's take cohomologies of the following guy. We take a Weil algebra of G, tensor it with a B, so it's a G differential algebra, and take space of basic elements. So let me recall that basic elements is the guys, here, that killed by our contractions and also invariant with respect to G. What is motivation to call it equivariant cohomologies? So maybe I could fit it here. Yes. So let us consider again our G manifold M, and let's be differential forms on M. Then equivariant cohomologies of B will be actually isomorphic to the equivariant cohomologies, but in topological sense. So we should take a classifying bundle of G, take induced vector bundle over M, and take equivariant cohomologies with respect to Z. So it's some topological information now encoded in this purely algebraically. And yeah, great. I could go first.
Andrey,
Yes.
I don't understand what is H of EG. What does that mean? I'm sorry. What is this EG?
EG is a classifying bundle for G, so it's a.
Oh, I see. Okay, okay. Classifying bundle for G. Okay, so you put that class. Fine. Over M.
Yeah, thanks. Here, I need it. Now I will introduce so-called the non-commutative version of this Weil algebra, but it will be non-commutative in the sense that it's doesn't belong to the non-commutative geometry. It's still classical stuff, but you will see. So the non-commutative Weil algebra, and it will be the main hero of today's talk, and we will quantize this object. Non-commutative Weil algebra. So now suppose that our Lie algebra has non-degenerate invariant symmetric bilinear form. So then we can identify G with its dual by its form. So example of such form could be, for example, Killing form over complex numbers. So we can define the Clifford algebra of G. And in a following way, we take a tensor algebra of G and quotient it by two-sided ideal. there is plenty of conventions. What you should put here, you could put 2, you could put -2, but okay. Some classical object, one of the simplest algebras, nice to deal with, and it's also featured deformation of exterior algebra G. So now, yeah. Such comments you can make probably without microphone.
Hey, Andre, maybe
okay.
if someone in general makes a comment without the microphone, you can just repeat it quickly so that us in Cyberville can figure it out. Okay, thanks.
Good idea. So it was missing plus here, so of course. Now, I want to state that this guy is G differential algebra, but first of all, I need some notation. So let xi will be some basis, be a basis of G. Then we can write our brackets in terms of structure constants. So we assume at the beginning that G is finite dimensional. So my f with 3 indices will be structure constants, and sometimes later I will often use Einstein notation. So if I will omit sign some signs and some by repeated indices. So let me define several guys that lives in the Clifford algebra. So GA will be just this guy. So some quadratic element, quadratic in the filtration, because Clifford algebra is not graded, but it's filtered. You now will ask me, Andrey, why we have a 3 lower indexes? Well, because we can use this bilinear form to lower 1 index here. So you have a metric, and you make from 1 2 tensor 0 3 tensor. So classical notation and differential. Should I write it more explicitly? And again, here's the sum over R and S. So it's a first guy, and the second guy will be cubic element. So cubic, because it's again lives in a filtered component free. I could actually write it explicitly, but there is no point. So now I'm ready to formulate, to define G differential algebra structure on my Clifford guys. So that's the example. If I will define, first of all, for 2 elements of my Clifford algebra, I will define a commutator or a joint action by just a simple formula. So let me remind you that Clifford algebras are Z-graded because basically when you look at this ideal, it is homogeneous with respect to Z2 grading on tensor algebra. So take your Z grading, take a model 2, you see quadratic, quadratic, 0. So this parity refers to that grading. So that's why my Clifford algebra is actually a super algebra. Okay.
Wait a sec, I'm slightly confused. Didn't you just say it didn't have a grading a moment ago?
It didn't have a Z grading, but it has Z2 grading.
Ah, okay, okay, thanks.
Well, how you construct it? You take the standard Z grading on tensor algebra.
Of course.
then
Yeah.
reduce it by 2. Then you can see that this ideal is homogeneous with respect to this Z2 gradient, because this is quadratic term, this is quadratic term, and this guy lives in degree 0 component. So
Sure,
they're
sure.
all
Okay. Yeah,
even with respect
gotcha.
to that. So that's why this is this supercommutator. So with respect to this notation, G-graded differential algebra structure is given by following formula. So contractions is just this adjoint commutator with respect to xi. Lead derivatives are given by adjoint commutator with g8, and differential in the Clifford algebra is given by the commuting with respect to gamma. More or less contraction part is trivial. Just plug in this definition and remember what is the multiplication in your Clifford algebra. So this guy will cancel each other and will be left only with a bilinear form. Just a good exercise for you. Derivatives take some time, but it's also good exercise. And I will speak a couple of words about this element gamma. First of all, we can compute the commutator of gamma with itself. So because it lives in degree 3 component, it will be odd. So it will be 2 gamma square. So they will not cancel each other. And this guy will be actually a scalar. 48. So this was shown by constant. And so, and you know, if you have in your algebra element that squares to in your superalgebra element that squares to 0, you can define a differential by commuting with it. It's again a good exercise to check that the square of differential will be equal to square to 0, and that will satisfy the Leibniz rule, the graded Leibniz rule. More conceptual. Now you're wondering, for example, how this guy appears here. There is a nice algebraic description for it. First, we know that if you'll consider invariance here, they are isomorphic to the Clifford algebra of Kaptan subalgebra of G. So it's a, do you see it? Okay. Now you could. It's this constant row decomposition and the statement of constant Clifford algebra conjecture. In a Clifford algebra, we have as subspace our Kaptan subalgebra. Because if you consider a vector space with a bilinear form, consider its Clifford algebra as a generating set, you have a vector vector space itself. Good. Now let us consider this famous element that called rho. It's a half sum of all positive roots in our Lie algebra. So that means that it belongs to the dual of Kaptan subalgebra. And now, using our bilinear form, this gamma will be just dual element to rho. Okay. Now, what we can do with this guy? So, starting from.
Can I ask before you maybe rub that off? I didn't quite get the definition of G differential algebra. So it's a.
So you should have a G differential space. So
B is the G differential space.
Plus, so you have a representation of that Lie superalgebra G has. So you have this Lie derivative, contractions, and differential.
Yeah.
And if your algebra, if your G differential space is an algebra, then if this representation takes values not just in any endomorphism, But in derivation of your algebra, then it's G differential algebra.
So super algebra B just means a superspace with an algebra structure as well.
Yes.
Okay, and I just have another really perhaps stupid question. So when you were defining the Lie superalgebra and you wrote these commutation
Yes.
relations, why did you only have to specify those ones?
The rest is zero.
The rest is zero. Okay, all right.
Sorry, I didn't mention.
Thanks.
So please. And of course, it will satisfy Jacobi, but I will make a bit small comment about that, but in the last part of my talk. Okay, now we know that a Clifford algebra is a G differential space. Now we want to try to make a non-commutative version of this construction. In a way, if you look at the Weil algebra, so symmetric algebra is a commutative algebra. From super point of view, exterior algebra is also super commutative algebra. So these guys are this algebra from super point of view is a super commutative algebra. What if you try to make it non-commutative? So first version, non-commutative version of exterior algebra is our Clifford algebra. And the non-commutative of version of a symmetric algebra of G will be universal enveloping algebra. So now we are ready to define what is a non-commutative Weil algebra. So as you can guess, it will be a tensor product. So I will define it by W beautiful. So we take universal enveloping algebra of G and tensor it with a Clifford algebra of G. Okay. Again, I claim that it's a G differential algebra, and I will give you a structure in a moment. So let's UI will be guys that lives in the universal enveloping algebra. So let me remind you that if you take that this algebra is generated by the elements of my original algebra G. So I define it here. And by abuse of notation, by axis, I will still refer to the same elements, but leaving in the Clifford algebra. Then I could write my Lie derivative as following, guys. So it's again will be Z. It will be super algebra. This guy will be purely even. This guy will have its own Z2 grading. So the contractions, as previously, will be taken only from the Clifford algebra. Well, before it was an exterior algebra, and the main hero of today's talk, we have a special element that calls cubic Dirac element. And so it's a cubic what is good about it? Well, we can compute its square. Then we will get the following stuff. So let's try to think what we got. So first of all, this is just a Casimir element of our Lie algebra G, and we know that this guy is a constant. So this square now belongs to the center of our non-commutative Weil algebra. That's why if we define differential as a commuting with this element, then it will square to 0 and satisfy Leibniz rule. So this operator, this element, or you can call it operator, was, I think, first it appeared in works of some physicists, but in algebraic context, it appeared in works by Constant. He used this element, for example, to relating. So you can compute the kernel of this guy on some representations. And this kernel will be related to the Euler characteristic of the corresponding homogeneous manifold. And the way how I presented it here was defined by Alexeyev and Meinrekin. They proved a new version of Dufour isomorphism in this game. But what is more important, such operator could be interpreted as a geometric Dirac operator. I will give a bit of picture, just a couple of, well, one board, how it could be done. And then in the rest of the talk, I will try to write a quantum version of it. By quantum, I mean 2D form. So a couple of words about geometric nature of this guy. It will be very sketchy, but I think
Andrey, I
yes.
just realized that, so you get an inner quantum differential calculus, don't you?
Well, it's not even a quantum. It's yes, it's a differential calculus on this guy.
Yeah, but it's inner because there is this element
Yeah.
given.
Yes, yes.
And you get you get the same also on the Weil algebra, like you get a commutative object with this very strange interpretation as non-commutative calculus, right?
Yes, all differentials that I will speak today will be coming from interaction.
Okay, thank you very much.
Okay. So, geometric interpretation of this guy. Let me recall you that the algebra itself could be associated with left invariant vector fields on our Lie group. And then the universal enveloping algebra could be associated with left invariant differential operators. So it will be some nonlinear expression with that with respect to our vector field. So it's left invariant differential operators. Okay, now we need a couple of definitions. So consider a vector bundle over some G manifold M, such that it's a bundle, a vector bundle of Clifford modules. Yes, I'm almost speaking about the spin structures. So given by the following, I take, so by Clifford modules, I mean the following. I have the representation of Clifford algebra on the cotangent bundle to endomorphisms of my vector bundle. And if I have a connection on this vector bundle, then I could define a geometric Dirac operator that will be some differential operator between sections of this vector bundle. Well, here I consider in the smooth section of this vector bundle. As a composition of the following maps. So I start with my sections. Now I use my connection. So I end up in the following space of sections. So it's a sections of tensor product of two bundles. Yes, it's my cotangent bundle. And then I have a structure of representation of a Clifford algebra on my cotangent bundle. So I use rho and end up again in the space of sections of my original bundle. Now, in this setting, if you will consider, for example, as a connection, Levich-Witte connection, then my geometric Dirac operator will be just the RAM differential process adjoint. Going back to the picture when I have my Lie group or some homogeneous space, this representation on the space of Clifford, this Clifford bundle will be given by the following guy. So I will draw here just to make the parallel. So I could think about Lie algebra of my group G as a tangent space. And remember, I assume that we have a form, so it's isomorphic to its dual. So this bundle of Clifford modules will be modules of a Clifford algebra of G. And I will get this mapping from this guy to the G invariant differential operators in this vector bundle. And with this identification, my cubic Dirac operator will be some geometric Dirac operator. And as I understand, it was almost 1 year ago talk by Braided, where he was using such constructions to define SU2 equivariant principal bundles. So I hope I didn't make the mistake, Braided.
G compact connected, but yeah, without lots of generality.
So that's why we want to construct a Q-deformed version of this Dirac, cubic Dirac element. So let's do it. Let me check how much I have. Okay. Perfect. So now Q-deformed part of my talk starts. So quantum group. UQ answer. Am I right that from 1 hour to 1 hour 30 minutes? Let me remind you that this guy is generated by the following methods: F, E, F, K, and K inverse. So it's a Hopf algebra, unital Hopf algebra generated by these guys. Just for sake of fun, I will write your documentation relations, but I will omit the Hopf algebra structure. What is good about this game? First of all, we know that the category of representation of this quantized version of SL2 is connected deeply connected actually with a category of representation of SL2. So let us consider the weight lattice of our Lie algebra SL2. So it's spanned by one fundamental weight. This fundamental weight pi is just 1/2 of a simple root. And we remember that if I will take a integrable guys, so meaning the positive part, non-negative part of this lattice, then for any weight, I could associate a representation. So is a finite dimensional representation of SL2. And the same could be done with its quantum analog. So there is a module over its quantized version such that it satisfies the following properties. So it's generated by the one element that called highest weight vector, such that if we act on it by E, it will be killed. If we act on it by K, it will be just multiplied by its weight. So let me remind you that this guy is a simple root, and on the space on the root lattice we have a bilinear form. So we can actually take any element in this lattice and take its inner product with respect to that bilinear form. So we'll get a number here. And in general, this is called a weight. If there exists an element of a weight lattice such that the following condition is satisfied for K, this vector called weight vector, and it has weight number. I will give you first simple and most important example of such representation that I will work until the end of the talk. So let's lambda will be 2 pi. And I forgot to tell that the dimension of the quantized representation and the classical one will be the same. So for SL2, it will be 3-dimensional representation. In the quantum case, it will be also 3-dimensional representation. Spanned by these guys, V-2, V0, V2. Let me note that if I will take its classical counterpart, then it will be G itself, but considered as a joint module over itself. So this thing we will try to quantize.
Andrey, there is, excuse me, there is something I don't understand. I missed what is P, span Z of pi, but pi is the fundamental weight.
Yes.
You seem, yeah, but you seem to call P plus, usually P plus is positive system. That's not a positive system.
Well, I mean, integral positive weights that give us
integral positive weights. Okay, okay. Sorry about that. Sorry. Thank you. Thank you very much.
Well, I mean, for SL2, everything is simple, so I try to keep it low.
No, I understand. Okay.
Now we will play with this representation, and we'll try to write an analog of that Dirac operator for this game. But first, I need some braided monoidal stuff. So, error matrix braiding. I will skip a definition of a braiding, but let me say a couple of words about it. So, let C beautiful will be a monoidal category. Then the braiding in this category will be a natural transformation between two functors. So tensor and its opposite, and it satisfies some additional conditions. So it's called hexagonal equations or diagrams. Roughly speaking, I could say that it means that my braiding satisfies Young-Baxter equation, but it's not a definition, it's consequence. For example, for my category of representation of quantum SL2 is a braided monoidal category. Where braiding is given by R matrix. So this R. Just to save time, I will not write the explicit formulas for it, but I will give you an example how it acts. Okay. So consider again this module. We know that its tensor square will be decomposed as follows. So in the direct sum of these three irreducible bits. And let's denote by W1, W2, and W3 the corresponding highest weights in these representations written in these terms. So then our R matrix braiding will multiply the first guy by Q squared, and by Schur's lemma, it will act by this constant on the whole module. For W2, it will be multiplied by minus Q to the power minus Q, minus 2. And on the third guy, we multiply by Q to the minus 4. So you see, classically, for example, when we consider the category of representation of SL2 modules, the braiding in this category will be just a flip. And this braiding, for example, when we will consider this adjoint module of SL2, we'll have only two eigenvalues, plus and minus 1. And this allows us to define what is exterior algebra and symmetric algebra. So just quotient by everything that is has eigenvalue 1, and you will get a symmetric algebra. When it's eigenvalue minus 1, you get exterior algebra. Unfortunately, here we have 3 different eigenvalues. So we don't have a hint what should be an analog of exterior algebra for this model. But there is a solution for this problem, which was done by Berenstein and Zvitsnagel in 2008. And I will give you a recipe here. So let this S2 sigma of some UQ SL2 module V will be the following. So it's all eigenvectors of the braiding such that eigenvalue of V with respect to our R matrix is bigger than 0. And the corresponding lambda of V will be, you probably guess. So it's the same, but the guy should be negative. So for example, maybe. For example, in our case, what will be in this symmetric square? So we should take a positive guess. So we should take this module and this module. And in second exterior power, we should take only this module because it has the only one negative eigenvalue. And we can define a quantum exterior algebra as a quotient of a tensor algebra by the corresponding ideal generated by symmetric square. Again, I will come back to my module and
So a naive question, Andrey.
yes.
Can one, is it hopeless to try to express these two guys as to sigma v, exterior wedge to sigma v in terms of braided commutation or anti-commutation relations?
It's a bit more complicated. Okay, the truth is following. So your braiding could be factorized in two parts. R1, R0 is a diagonal part. R1 is an nilpotent. So it will be something of the form 1 tensor 1 plus the tail that belongs only to this guy. Okay, then you can construct a new operator by taking this horrible expression. Yes. And using this operator, you construct a new, new natural transformation between tensor product and its opposite, Z, which is given by following formula. So this construction, well, this operation, this D appears already in the work of Drinfeld about quasi-Hopf algebras, and it's closely related to Kova-Andrey-Hopf algebras. The square of this guy will be identity, so this guy will have two eigenvalues, plus and minus one, so it will be plus one guys, it will be minus one guys.
And is there any relation with these braided permutations that like Majid uses in his picture of Voronovich's prolongation of a back-covariant differential calculus?
No. It's a bit different story because you can use this braided permutation for something that satisfies Young-Boxster equation. This operator sigma will not satisfy Young-Boxster equation.
Okay.
It will satisfy, so it will be connected not with a braid group, but with a cactus group.
Okay.
I couldn't say much details about this cactus group, but it's some funny stuff going on.
Thank you.
Okay, now I will try to find my notes. Ah, 11, yes. For our beloved modules, the module, the commutation relations will look like follows. So if you wedge V2 with itself, it will be 0. If you wedge V minus 2 with V minus 2, it will be 0 again. If you wedge 0 V0 with itself, it will be something fun. And so V minus 2 wedged with V2 is just minus V2 wedged with V minus 2. If you will excuse me, I will delete this guy, erase it. and we'll leave some space here. Okay. Then v minus 2 wedged with v0 has a q in front. And v0 wedged with v2 has minus also and minus 2. So it's some Q-deformed version of the stereo algebra. What is good about it? It's of PBW type. It has the same dimension as exterior algebra for G. And we can try to construct a Clifford algebra based on this game. Well, now we have an invariant form on our model such that it satisfies the following conditions. So it's unfortunately not symmetric anymore. It's bilinear. It's not degenerate. You see symmetricity falls here, where C is some complex parameter. And to construct a quantum Clifford algebra of it, we can deform this multiplication by this bilinear form. So I will do it here. So I defined my Q-deformed Clifford algebra of this module as a tensor algebra of V, quotient by the following relation. So I will use this notation of the operator sigma. So I just following the classical picture. I have an algebra, exterior algebra, I have a bilinear form. So I use this bilinear form to deform my exterior algebra. Yes, yes. Yeah. The first social gradient will be exactly what. And what it will get. So we will have some additional terms here. So this guy exists on the Clifford algebra and also here. So let us try to study this distance. So it's a nice non-commutative algebra with a lot of Q everywhere. I actually we are doing it by the recipe. I don't know, it was already considered in 90s. So you start with some exterior algebra in some braided modular category, use a bilinear form to deform it. So very fancy stuff. But for this particular case, I want to manifest the following law. First of all, my Q-deformed Clifford algebra is a direct sum of two ideals. Second of each of the ideal is isomorphic to algebra of endomorphisms. And dimension of the spaces S1 and S2 is equal to 2. So that's amazing because as we all know about classification of simple central associative algebra, if I have something that is sum of endomorphisms of two-dimensional space, then it's just a classical Clifford algebra. So just as an algebra, this thing is isomorphic to Clifford algebra. which is very amazing. Because you start with a lot of Q's everywhere, but you end up to the same classical object. There is some conceptual, of course, interpretation of it. Again, Clifford algebra is not Hopf algebra, so we couldn't deform it by means of Hopf algebras. And we can deform it, for example, using this Gerstenhaber approach. So we should compute some cohomologies. And if we compute these cohomologies, we can figure out that there is no deformation of classical Clifford algebra. So it's very nice. Notice that for such simple example, I didn't see anywhere in the literature, because when I was looking for preparation to start this research, there is a lot of approaching what is a Clifford algebra in non-commutative case. And they all based on some variable constructions, but not so many people noticed, well, probably nowadays, that it's actually just a Clifford algebra, the regular one. Okay, good. Now I promised you to write a Dirac operator, exactly this board. So, but before I should define what could be analog of Lie derivatives and contractions in my Clifford algebra. Because
Before
remember, of course,
sorry,
no.
Yeah. Sorry, Andrey, just before you continue, sorry to interrupt, but in the lemma, sort of what's the logical order of things? Like, does the decomp, like, do 1 and 2 follow from 3, or do 1 and 2 have a meaning before without 3?
Well, you start with 2 because you have some element that you called gamma, and I could write it explicitly. Okay, let me.
So do 1 and 2 make sense without like 3?
Yeah.
Okay.
But 3 is just a direct consequence of first 2 guys.
Sure. Okay. Thank you.
Give me a second. Okay, I'm back. So, could you point it on here? So, first I want to define what is a analogs of Lie derivatives here in this quantum Clifford algebra. Let me remind you that as module over itself, or as a UQ of SL2 module, this guy could be embedded in the UQ of SL2. Because as in the classical picture, so as it decomposed into direct sum of all finite dimensional representations. And it will be that's it for the non-quantized version. But in the quantum world, unfortunately, we'll also have some infinite dimensional guys. There is infinitely many of them. So there is a particularity of of quantum groups that the universal enveloping algebra doesn't look so good when we look at the UQ of G module over itself. You would ask me how I define an action here. So it's given by the so-called adjoint representation. So if you have a Hopf algebra, the adjoint, in this case, left action is defined in the following way. So I'm using Fiedler's notation here. So I take a co-product of my element A, and it's right and left legs, and here it's written as. So with respect to this embedding, I could write my elements of my beloved module V2 pi as follows. So V2 will be just E, V0 will be this guy. One could think about it as a Q commutator. But V minus will be this. So now I can consider the following algebra. I could take V2 pi, and as a multiplication, I will take the adjoint multiplication. And this guy will be close with respect to this multiplication. So now I could define an action of this guy on my Clifford algebra via following commutative depth. First of all, I know by construction that my Clifford algebra I think I was writing here is a module over UQSLT. Then I could embed my A via this identification, and this will be my representation rho of A on my Clifford algebra. So my analogs of Lie derivatives, now it will be a Lie derivative with respect to elements of A. So basically with elements of V pi stores. Well, remember, as a vector space is just our module. And this guy is quantized adjoint representation, so we could think about it as a quantized version of our Lie algebra. Good. What about contractions? Contractions, as usual, easy. But before we should probably speak about, yes, about these guys. So I could define some commutators in my Clifford algebra that I will call sigma commutators. So since it's a work in progress, we're expecting preprint to be ready soon. I'm not so sure that it's a nice term for these commutators, but if you have a better advice, I will be happy to follow. So I will define it in the following way. So I take multiplication in the Clifford algebra, then take a sign, because again, it's the super algebra. And before I take in multiplication again, I apply my sigma. That's how people, well, somebody will call it braided commutators or something like that. Then my Lie derivatives, as in the classical sense, could be represented via these braided commutators by the following formulas. So this element will be analog of this elements, quadratic elements that it will call in the classical case G. And for the last guy, and it's all my sigma commutators. I mean, using this sigma commutator, I could define a differential. Because as well as in the classical case, I have a cubic element in my Clifford algebra such that its square is equal to constant. So I have a gamma such that it squares to constant. So I could define a differential by taking a sigma commutator. And because my gamma is also invariant, so it's not a even squares to some constant, but gamma belongs to invariant part with respect to action. In fact, this commutator will be just commutator. But if you think about it for a while, what this guy do with the trivial modules, it will be clear for you. So again, it will be some inner differential. And contractions. Because of the way how I defined my multiplication and Clifford algebra, they could be written as you expect. So it's just a sigma commutator with the guys with a minus. Again, a nice exercise for your post-seminar tea or beer. Do it in the classical sense, and you will see that it will work on here. So, could you see it? No. Everywhere is sigma commutators and lemma. If you define everything like that, we have a Cartan magic formula. And again, because differential is somehow corresponds to the trivial module, it will be actually not the sigma commutator, but just the usual commutator. Amazing. Now, the final accord of my talk, is this cubic guy. I think I should write it here. Cameraman. So cubic U-deformed Dirac element. Following Burdick, and his collaborator, Burdick from Czech Technical University, they found a nice set of generators for UQ of Hassel2. It will be X, which is exactly our V minus 2. Well, Z, you can guess that it's V0. Y, it will be V minus 2. We also have a Casimir element that I will define by Cas. Let me remind you that it's a generator of the center of UQ of SL2. And the last guy is just K. Okay. Then let me speak about a bit about tensor product of algebras in braided monoidal categories. So if I have two algebras A and B in a braided monoidal category, for example, in the category of representations of UQ of SL2, then to define a multiplication on the tensor product such that it will be again multiplication in this category, I should play a bit. So this multiplication is defined in the following way. I will write it from the left-hand side. It will be easy. Oh, well, probably I will write a diagram. So this multiplication should involve braiding. Let me draw a picture. So we want to multiply two elements, one in A tensor B, and another guy is in A tensor B. What we should do first? We should swap these two guys. To do it, we should use braiding. So I use this diagrammatic calculus. So now we have A here, B here. Then we apply our multiplication map. To each of the guys, and we end up in something that lives in A tensor. Pretty easy when you draw diagrams, quite hard when you do computations. So my non-commutative Q-deformed via algebra will be the following. So maybe better. The Q-deformed non-commutative via algebra is the following guy. So it will be W beautiful SL2. So I take UQ of SL2 and tensor it with this nice Clifford algebra with a quantized adjoint module. And my multiplications here looks terrible, but still you can do some stuff. I'm claiming now that first of all, it's easy to see that it has some Lie derivatives. As you expected, you have a joint action here, you have a Lie derivatives here. It has contractions. Well, you do nothing here, you contract here. And you define differential with respect as a linear differential with respect to this cubic element. Well, analog of the cubic element that looks almost the same. So I will write it and then I will explain what is going on. Plus some terrible coefficients that I don't want to mention, but it's some expression in Q and Q inverse. Okay. Okay, I already erased everything. Yes. So let me remind you that the classical cubic Dirac element looked like as follows. It was Casimir, something that looked like a Casimir element, plus this guy, one tensor gamma, where gamma was that cubic element that was given you differential. So here you can see the same. This guy defined a differential in our Clifford algebra. Well, this Casimir is a bit mysterious here because classically we had one here. And this guy, well, remember that X is actually V2, right? And we had our form that says that pairing between V2 and V minus 2 was non-zero. So it's basically a sum of a dual basis. I take some guys in my UQ of SL2 and take the corresponding dual element in my module. So that explains these coefficients. And ta-da! If you will compute its square, then of course, again, it will be some terrible coefficients in Q's. But, well, of course, to be honest, I should write here tensor 1, plus 1, tensor 1. Which means that this element is actually central and it defined differential. Now, there is a question, still open problem, how to interpret this coefficient that I don't want to present, but that's why it's a work in progress. So now I hope this guy could be applied to, for example, in the stuff that Branimirs do, and also we're expecting to have some nice presentation theoretic application of this guy. That's the end of my talk. Thank you very much.
Okay, thank you very much, Andrey. So any questions either here or the audience online?
Could we use this to prove a version of Dufour's isomorphism?
Dufour? Pardon, Dufour isomorphism. Could you please repeat the question because I didn't hear it.
Could we use this as a tool to prove a default version of Dufour's isomorphism?
Yes, that's our plan. Yes, so probably it wasn't so clearly for the audience in the room. So one of the plans, we want to prove the quantum version of a Dufour isomorphism, which give. So I just repeat to you what it is in the classical sense. If you take symmetric invariance here and center of enveloping algebra here, then there is a non-trivial map that's called Dufour isomorphisms that establish isomorphism between these two guys, not just as a vector spaces, but also as an algebras. And Meinrekin and Alexeyevsky was using this guy explicitly. One of their goals to prove to give a new proof of this guy. We will try to make a quantum version of it. So to put Q here and here.
So is there any difficulty to define it on any quantized Lie algebra rather than SL2?
Yeah, thank you for this comment because I forgot to say it in the talk. If you want to extend this technique to other quantum groups, we'll face a problem because if you will look for exterior algebras, for quantum exterior algebras, they will have not the same dimension as the classical one, and the whole construction with the Clifford algebra will fail because, for example, they will not have a PBW basis, so it will be not the right object. But we are proposing to look on the problem from a different side. One of the main hero of the second part of my talk was this Clifford algebra. So it looks like that the right object to begin with in a Q-deformed setting is a Clifford algebra of G. So you can think about it as endomorphisms of the corresponding spin modules, or, for example, use some fancy stuff like a constant rho decomposition. And then starting with this object and defining a filtration on it, we can probably find a new way how to define good exterior algebras in Q-deformed sense, because we will have some filtered algebra that behaves nicely. We take associated graded algebra and it will behave nicely again. But there will be some future projects.
Thank you.
So is Q-deformed commutative while algebra of any interest to you?
I think yes, it will be. It should play a role here.
Yeah, but besides this,
probably yes, but it's kind of we wanted to rush to write this cubic Dirac and try to apply it in the non-commutative geometry.
yeah, just in connection of the equivariant topology interpretation.
Yes. But maybe it should be used in the careful definition of this filtration on the Clifford algebra. But it looks like that it's more natural to start with this non-commutative well algebra and then take associated grade.
So I have a bunch of questions. I'll try to be as efficient about them as possible. But first question: if you look, considering this v sub 2 pi, which you're identifying as sort of quantum adjoint representation, if you take its dual, I mean, can you build from that some sort of reasonable calculus on SUQ2?
Well, probably yes, because you should tensor it with spin module and it will be some calculus. I expect it will be Heckenberger and it will be not Heckenberger and Cope. It will be expected it will be something, of course, not bicovariant, but left covariant. But I expect that it will be the same calculus that appears, for example, in Podler sphere, if you restrict it to Podler.
So I guess you have in mind then, so that lemma you gave, I guess, gives you it gives you some spinor modules that in principle you could try to use to build up a geometric sort of Dirac on SUQ2 using speeds.
I believe that what you told to us in Zagreb just before COVID should work. So it's probably the right guy. It's just written now a bit obscure with a lot of Q's and coefficients, but we just start trying to commute things.
So in that regard, then, is there an analogous object like a cubic Dirac for like UQ squared 1? Because there would be like, I guess what would be like a sort of magically perfect is like if you had you could think about the Cartan inside SUQ2, and then you had a relative, you had the cubic Dirac of UQ squared 1, and then a relative cubic Dirac of SUQ2 relative to the Cartan. And
yeah, for this it's already done by Peter Sonberg and Pauli Pančić.
Okay.
So relative stuff is covered.
Okay.
For SL2. And it's again the same story that, of course, you have a very small subalgebra. K will be Cartan spanned by K and K plus, but your P will be two-dimensional. And again, the same story happens with the Clifford algebra. It will be classical.
Okay, and one final comment that's conditional in answer to his very silly question. This funny Casimir element, is there a well-defined limit as Q goes to 1?
Yes, you can think about it as a following guide. So on you have a bilinear form on G, right?
Yeah.
So it means that you have an invariant element in symmetric square of G. This will be exactly this guy, more or less.
So, but the I mean, and that's this Cas that you write down. This strange
this Cas.
Yeah.
Yes. Well, I should be a bit careful, not exactly this Casimir, but you should add something, and then it will reduce to the classical Casimir.
Because one's almost tempted. Sorry, please.
I could show you. As usual, problem will be with the case. You can see that if I will take a limit, Q is equal to 1, this will be 0. But you can do some magic and make it in the limit looks like a Casimir for SL2.
So it's this thing, not its square, that gives rise to that appropriately fudged gives you the classical Casimir in the limit.
Yes.
Okay.
That's why that's one of the surprising facts for this cubic guy. So it give you its square give you not just Casimir plus something. It's a square of Casimir.
Okay.
That also this Casimir appears here, so maybe that's the reason. I don't have a conceptual explanation for you why there is a square.
Okay, thank you.
Okay, great. Any more questions? Yeah. Doesn't look like it. So okay, let's thank the speaker again. And I'll pass it over to Karen.
Oh, wow.
I can't accept, I don't think I can announce my own talk, but I will speak next week. It was supposed to be Suvrajit, but he was not able to make it, so I'm taking over. All right, so hopefully see you guys there, and hope everyone who's in Prague can have a pivot on my behalf, since I can't.